Hi, this video is going to walk you through the notes associated with early quantum theory and models of the atom. In this video, we're going to talk about how the quantum hypothesis began, what its origins were, and then talk about some fundamental concepts behind quantum mechanics, which include the interesting wave-particle duality concept. Then we'll also take a look at atomic spectra and how quantum mechanics led to what we call the Bohr model, and then an even finer tune to the Bohr model with the de Broglie hypothesis. So this is a bit of a walk through history as we talk about the connection between light and matter. And it was known that we could generate sort of these cathode rays by taking an evacuated vessel, so some kind of glass tube at very low pressure, and setting up high voltage between two terminals. So this cathode and anode, and these are old terms, but anode means without negative, so that's why it's positive. And cathode is the source for negatives. And by applying this high voltage, it was observed that you could get this area to sort of glow. And the way that would work is you'd put like a phosphorescent paint on the inside, or just kind of under low pressure, just inject some phosphorescent molecules to coat themselves on the inside of the glass. And then under high voltage, there would be pieces of the glass that would sort of light up. So a refinement to that was to put a couple of screens. And these screens would filter out most of the particles that were being emitted from the cathode. But the ones that are allowed to go through were traveling relatively straight. So now we could just concentrate on putting the fluorescent paint right on a single part of this cathode ray tube. And then under high voltage, these particles, it was observed that they would accelerate. You increase the voltage and you would observe the effects here. So cathode rays really, as we know them today, are electrons. So electrons are being emitted from this metal surface and then colliding and with this phosphorescent paint and making it glow. So this is one of the earliest signs of the connection between matter and light. Where we have electrons, matter, traveling and then having an interaction that causes light to appear. Now the cathode ray tube actually, if your folks have any really old TVs laying around, they're really bulky and they're really thick, it's because they're cathode ray tubes. And the way it would work is that, again, you would have high voltage here, and electrons would accelerate up to high speeds. Then you have a couple of plates that would sort of take out most of the electrons, except for the ones that were traveling very, very straight. And then with a combination of electric fields and magnetic fields, you could steer the beam wherever you want. So on the original TVs, what would happen is that the magnetic field would sweep a beam of electrons horizontally, and then that process would be repeated, but deflecting the beam slightly up based on the electric field between these two charged plates. And synchronizing these, you could actually paint the screen relatively quickly. So you'd still have fluorescing material here on the screen, but then you would draw across it really, really quickly. So the magnetic field would steer the beam from left to right, and then the electric field would steer it up and down and actually paint the entire surface at around 60 times a second, which is much faster than the persistence of vision. That's around like 15 hertz, something like that. That's how fast you need to move something digitally, like if you remember those old flip books, right? So you draw an image that's slightly different on page after page, and then you flip through it and it looks like the object's moving, especially if you do it fast enough. That's called persistence of vision. So this is how original TVs worked, but they're very bulky and not very efficient. Blackbody radiation was another topic that showed the connection between matter and light. Really what blackbody radiation means is that, I know it sounds weird, black body and then radiating, but it has to do with considering a surface drawn around a glowing object and taking a look at how the temperature corresponds to what the peak wavelength is. So in this graph, you can see the green around 6,000 degrees Kelvin. That's about the surface temperature of the sun. And that is the peak wavelength produced by our sun is green. So you might want to think about that next time you take a look at those green leaves out there. Now, the peak wavelength, this is our visible light right here, it was observed for glowing objects that usually we're used to things glowing, you know, kind of glowing red or something like that. Like if you have an electric burner on the stovetop, it appears red when it's glowing. That's at a relatively low temperature. So this is called Wien's law, and it shows an inverse relationship between the wavelength of light and temperature. So as the temperature increases, we see the peak wavelength going further and further towards the blue end of the spectrum. And of course, you probably remember this from chemistry, is that the Bunsen burner, the blue part of the flame, is the hottest. Now, in a quick study I did with light emitting diodes, I created a graph that shows the voltage applied to the LED and the current drawn by the LED. And you can see these currents are very, very small, on the order of tens of milliamps. And there is, you know, straight lines being formed, but that's Ohm's law, of course. So the slope of this is going to be the resistance of the LEDs. And you can see they all have approximately the same resistance, about the same slope. Now this was 5 different kinds of LEDs. So up here, this was ultraviolet. Ultraviolet LEDs are used to check for things like sometimes blood spatter or verify authenticity of currency. And then here we have red, yellow, and green LEDs. They're all kind of bundled together. And then this is infrared. But what I was most interested in is the threshold voltage, because light emitting diodes are semiconductors. They only conduct under certain conditions. They need a threshold voltage. So if you extend this line back and find its y-intercept, then we can compare that to the wavelength for these different LEDs. In this chart, we take a look at the threshold voltage, which means the minimum voltage needed in order to allow the LED to conduct and produce light. And then take a look at not only the wavelength, but the frequency as well. So plotting the activation voltage for these LEDs versus the frequency of light, we actually get almost a straight line, which implies that there's a linear relationship between the energy carried by light and its frequency, which is also backed up by Wien's law. Again, we saw if there's an inverse relationship between wavelength and temperature, then there's got to be a direct relationship between frequency and temperature. Wavelength and frequency are inversely dependent on each other. And you can actually calculate the slope of this line. It's a very, very small number. But again, this is the main idea, is that there seems to be some kind of direct relationship between the energy required to produce light and what its frequency is. That's another really big clue. So now we take a look at the original quantum hypothesis. What is light? Is it a wave? Is it a ray? Is it a particle? And if we take a look at those 2 pieces of evidence I just shared with you, how do you connect frequency to energy? And at the turn of the 19th to the 20th century, Max Planck said, well, let's just try, you know, a thought argument. Let's just suppose that the energy associated with light comes in bundles. If there's a direct relationship between frequency and energy, if there's a linear relationship, then let's just say, hey, there's a linear relationship, and we'll put a number in here. And it's now called Planck's constant. So what is that number? Well, again, we could actually verify that through experimentation. These LEDs have a threshold voltage, and as the threshold voltage increases, the frequency of light that they produce is going to be different. So notice that this was infrared, the lowest activation voltage, and then visible light, kind of all very similar, kind of clustered there, and then this is ultraviolet. So the value for Planck's constant is a very, very small number, which makes sense. So we now look at the birth of the word quantum, because energy, if it's proportional to this very small constant times frequency, is going to be a number. And that means that the energy that's carried by light is going to be quantified, even though it's a very small number, but it is a number. It's not a random number. It's not infinite. So this is the quantum hypothesis, that the energy carried by light is going to be a single number. Now, if it's a single number, that means it can't be a continuous wave. The wave itself must have limits. So we're just going to take note of these two constants. This one is joule seconds, and this is electron volt seconds. When we're talking about electrons, actually, this constant, the electron volt seconds, is much more useful. So a quantum is really the smallest amount of light, which kind of makes sense, because over history, if we think about the word atom, and the word atom comes from Greek meaning indivisible. And what an atom, the concept anyway, was, say if you have a bar of gold and you cut the bar of gold in half, then you have two pieces of gold, right? So if you keep on taking one of the pieces and dividing it in half and dividing it in half, then you have smaller and smaller chunks of gold. But eventually, you know, from a theoretical standpoint, you're going to get to a point where you can't divide it anymore and still call it gold, because you'll have a fraction of an atom. Now that's not, if you were able to divide it, you'd have two different elements now. Because of course an element is identified by how many protons it has, its atomic number. So here with Planck's hypothesis, that means energy is also quantified. So if we take light and then kind of divide up the light smaller and smaller and smaller, eventually we get to a point where you can't have any chunks that are any smaller. And that's what one quantum is. Now, in everyday language, sometimes people say, ooh, that was a quantum leap, you know, implying something really significant, earth-shattering. But actually what a quantum is the smallest possible unit of energy. It's actually a definition of smallness. How small can you get and still have something? So anyway, beware of that when you hear somebody say, ooh, that was a quantum leap. All right, well, here we go. Well, so yeah, what about this wave then? How can you have a wave that has a limited duration? And the answer can come mathematically by adding frequencies together, adding a set of frequencies that are harmonics of each other. And if you look up localized wave packets, you can actually see how you can use math in order to build this. So we actually have wave functions that are built by adding together harmonics in such a way as to cancel the wave out in most of space, but then have constructive interference over a very small amount of space. And that's how come we can have a particle. Instead of being a continuous wave, it's a wave packet. And the wave packets contain an energy equal to Planck's constant times the frequency. Now this is seen very obviously and what's called the photoelectric effect. And I'm going to have a separate video that talks about the photoelectric effect. But essentially the idea is that light, typically of very short wavelength, high frequency and high energy, when shining on a metal surface can actually emit electrons. And that's what we opened with when we talked about a cathode ray tube. And by applying a positive voltage, these electrons will get accelerated. And so light can actually cause current to flow in what we call a photocell. However, the threshold in order for this to occur depends on the frequency of light. Again, the connection of frequency to energy. And I'll talk more about this in another video. Now, if a photon can have a collision with an electron, because that's essentially what's happening, is that you have this particle of energy that hits an electron and essentially ionizes it, so it becomes liberated from its original atom, then that implies some kind of collision. And you know that some of our fundamental concepts about conservation of energy and conservation of momentum must always be the case. And that would imply that light actually has momentum. Well, if it's got energy, then it should have momentum. And here's how you can calculate the momentum for a light particle. So it's directly dependent, once again, on the frequency of light and inversely dependent on the wavelength. But that's really interesting because when we apply conservation of momentum to a collision between a photon, that's a light particle, and an electron, then that implies that conservation of momentum occurs. So when light interacts with mass, we see a couple of different things that can happen. So one is photoelectric effect, where a photon is completely absorbed and an electron gets ejected or ionized. So we would call that ionizing radiation. That only happens with very, very short wavelength or very high frequency. Now also the photon might be absorbed by the electron, but not have enough energy to eject it, and then the electron would move into an excited state. More about that to come. And the photon could also scatter from an atom and lose some of its energy, or the photon can produce an electron-positron pair. Once again, this is predicted by conservation of momentum, where we have a photon that's traveling by, and for some reason, and there could be lots of reasons, but an electron is ejected and a positron is also ejected. A positron has the same mass as an electron, but has a positive charge. This is actually first observed in a bubble chamber. What a bubble chamber is it's a pool of liquid nitrogen that's allowed to expand quickly. And here we see a photon coming in and a positron created and an electron created. And these curls that we see happen as a result of the fact that there's a magnetic field established. And one of the things we didn't really get to talk about during this semester, but is observed, is that those charged particles moving in a magnetic field are going to feel force perpendicular to their velocity. And of course, we know if you apply a force perpendicular to the velocity of something, it's going to move in a circle. These circles spiral in opposite directions because they have opposite charges. And they also decay and they get smaller and smaller because they're losing energy as they're traveling through this liquid nitrogen. Now this is a gamma ray. A gamma ray and X-rays are on the same order. And you know, of course, if you go to the dentist or have an X-ray, people are very careful about X-rays because they're very, very high energy. They carry ionizing energy, essentially. And that's not something that you want to happen to your body in an uncontrolled way, because it can interfere with cellular structure and reproduction. Right, so what is it? We observe that light has wave aspects to it, but we also observe that it can collide with an electron, which implies it's like a particle. And so we're kind of stuck with that. And so we're just assuming that if you design an experiment that looks for the wavelength of light, it'll look like waves. But if you design an experiment that looks for the particle aspects of light, then it'll behave like a particle. So we are stuck with that. It's called the wave particle nature of light. Now, if that's the case, though, if light could behave as a wave and a particle, then what about mass? Can mass have wavelength properties? And the answer is yes. Anything that has momentum is going to have a wavelength, and you could design experiments that show the wavelength property of light. But as you can see from this equation, we just take the momentum equation and solve for wavelength. Planck's constant is the numerator, and that's a very, very small number. And compared to, say, your momentum, if you're just running across an athletic field or something like that, that means your wavelength is going to be very, very small, and it's impossible to really design an experiment that's going to demonstrate your wavelength properties. But if it's an electron and the momentum is very, very small, then it is quite possible. Right. Now let's talk about models of the atom. It was known that matter had both positive and negative properties that you could separate somehow. So you might have talked about this in chemistry class with one of the most significant experiments in understanding the structure of the atom. Ernst Rutherford designed an experiment where fired positively charged particles at a very thin layer of metal and wanted to see what happens based on that. So alpha particles are essentially helium nuclei. So this is helium that's been stripped of its electrons. And that's pretty common. There are a number of different radioactive sources that are found in nature that produce alpha particles. So having this radioactive source encased in some shielding to prevent alpha particles from just going everywhere, and with a small hole drilled in it, then we can count on the fact that the alpha particles coming out are going in a relatively straight line. Now, here's our metal foil, pounded out so that this is relatively small number of atoms thick. And then these alpha particles collided with the atoms in this metal foil. But surprisingly, most of them just went straight through. And every once in a while, one would actually bounce back relatively strongly. So this was a big surprise. In fact, the observation of this was done by 2 graduate students, and they had to do it very late at night when it was very dark because this viewing screen was fluorescent, and they would wait and look for the little flashes of light to occur and then mark down how many flashes at what angle. Pretty tedious work, but the grad students were actually pretty clever, and they came up with a way to do this more automatically. So they came up with a device that could measure the presence of radiation very specifically. Their names were Geiger and Marsden, and now their invention we call the Geiger counter. And so instead of looking for flashes of light on the viewing screen, they would listen for clicks. So the conclusion from Rutherford's experiment was that an atom is actually mostly empty space. And this scale is really obviously not appropriate because if you take a look, the difference between the radius of the nuclei and the radius of the electrons in orbit around that nuclei differ by 5 powers of 10. So this diagram is not accurate to scale at all. If you were a nucleus and you had some electrons, your nucleus is here in Essex, your electrons might be, you might have one in St. Johnsbury or Rutland or Montreal. So the scale is very different. Now, another interesting invention was neon lights. And again, this is a turn of the century invention, which says that, well, let's build on this cathode ray tube and try different kinds of gases inside it. So if you take a relatively pure sample of gas and inject it into this evacuated glass tube and apply high voltage, you would observe that different elements would give you different colors. Now, you probably observed this when you did a flame test in chemistry. So it's important for us to then think about what the spectra looks like. This first spectra looks to me like a hydrogen. Actually, okay, hard telling, not knowing. But this might have been one of the things that you've done in chemistry when you did a flame test, is you would look for the different wavelengths that are present. So the atomic spectra was a huge clue about the structure of the atom. And in fact, it was observed that the spectra followed some kind of regular pattern. That pattern was observed to fit sort of an integer model. And you could predict the wavelengths by taking a look at this series. Now, what it means is that one over the wavelengths could be found by taking this constant, which probably has the speed of light as part of it, and then running through different numbers. So if n is equal to 3, then you have 1 over 4 minus 1 over 3 squared. And that's a pretty big difference. But then as the numbers increase, then we wind up with wavelengths that aren't that different. And it was observed that for the different parts of the hydrogen spectrum, the ultraviolet part and the infrared part, they also followed a similar series, but the starting number was different. It was a lower number for ultraviolet and a higher number for infrared. And now we know these two values for n as the principal quantum numbers. So that if we put these spectral lines together, and again, this is just hydrogen, this is what we can see visibly. You can still measure the infrared and the UV by using some electronics, but you can see that on the low end of the spectrum, there's a big jump between lines, but then they get kind of packed together. So Niels Bohr took the Planck quantum hypothesis one step further and said, well, if the energy from a photon comes in packets, and we imagine this sort of planetary model with an electron in orbit around a positively charged nucleus, then maybe these orbits aren't continuous. Maybe it's not every orbit possible, like the way it is with gravity. If light is quantized, then maybe these orbits also have to be quantized. So once again, taking a model and running through some numbers, it also suggested that if energy is quantized and there are only certain orbits possible, then that means angular momentum also has to be quantized. And these n numbers for angular momentum, you actually used in chemistry when you used Hund's rule to find out the order in which electrons are going to fill up orbitals in the ground state. So once again, in this planetary model, we can assume that there's some kind of Coulomb force in between the two, and that's going to drive the orbit. And in this case, we take sort of any possible nucleus available by using Z. Z would be the atomic number, and then Z times the charge for an electron, the fundamental charge constant, 1.6 times 10 to the minus 19 coulombs. So that would give us what the size of the charge is at the center. So the force is actually the product of the two. So K, this is Coulomb's law, Q1, Q2 over R squared. I jumped a little bit. Then if we take those quantum numbers and plug them in, it turns out that only certain energy levels are available for hydrogen, and that does a nice job at explaining the hydrogen spectrum. So it's transitions from one orbit to the other that reflect what the energy is for that light particle. So ground state for, again, this is hydrogen, so that's only one electron. And the ground state is minus 13.6 electron volts. Electron volts is the unit of energy. So that means that since it's negative, it's in a bound state. We talked about that earlier. To get to a free state, then you would have to add 13.6 electron volts or more. And then once you add that to this electron, it's going to pop up here into the free state region with a positive energy. And then it's going to be able to zip around freely. So you will have ionized that hydrogen atom if you apply 13.6 electron volts to an electron in the ground state. Now, if you apply less energy to it, then it might go into an excited state and then later drop back down and emit a light particle as well. So you can see this actually nicely explains the atomic spectra for hydrogen. That our visible light, right here, the Balmer series, are transitions from higher energy states down to n equals 2. And the ultraviolet components of the spectrum are transitions from higher excited energy states down to n equals 1, the ground state. And then transitions from higher energy states down to n equals 3 are infrared. They're smaller energy drops. So the correspondence principle just suggests that that the difference between quantum levels from different energy states are pretty small. And the final topic then is the de Broglie hypothesis, which takes the Bohr model and fine-tunes it just a little bit more. So de Broglie was a French physicist who was working on some concepts theoretically around atomic theory, and was fascinated about this idea about how the Bohr model explained hydrogen spectra. But since angular momentum should be quantized and energy states should also be quantized, he came up with a different way of looking at this. So if the momentum of the electron also has a wavelength, is there a connection between the wavelength and the orbit itself, the physical orbit? And he posted this as part of his doctoral dissertation, but his advisors were kind of blown away by this idea, and they didn't feel like they could actually put their stamp of approval on this concept because it just seemed a little too far out there. And so his advisors contacted Albert Einstein to read his thesis and give his thoughts about it. And Einstein thought his ideas were great. So this is, so not only did Albert Einstein read his doctoral dissertation, it was nominated and won a Nobel Prize. So we think this is the only doctoral thesis that led straight to a Nobel Prize. So what is this de Broglie hypothesis? It has to do with electrons, but also has to do with wave-matter duality. And he suggested that electrons actually were probably in standing waves around their atoms, and that the principal quantum number tells you how many wavelengths are present. So for n equals 2 in that excited state, then it oscillates back and forth 2 complete times, 2 waves. So here are the main ideas. Number 1, quantization of energy as far as light's concerned. Direct evidence of this came from Wien's law came from the photoelectric effect, and that implies that we could think about light as a wave and as a particle at the same time. So both matter and light have wave and particle properties. The atom itself actually is mostly empty space. And so that idea about matter that we think about is really just electric forces holding things together. And line spectra match up with energy level transitions for electrons. And what we call the ground state is the lowest possible energy. So that's a quick rundown. And I'm going to post a couple more videos that talk more about the photoelectric effect and the Bohr model.